Okay, let's start with the big picture. The title is Data Center Network Routing Protocols, enabling high performance at scale, exploiting path diversity and dynamic scheduling for modern cloud workloads. What does this mean in simple terms? Data centers are like super-powered computer hubs that run everything from your email to AI apps. Unlike old-school office networks where data mostly comes in and out, north-south traffic, data centers have tons of data zipping around inside between servers. That's called east-west traffic. This happens because modern apps, like searching on Google or analyzing big data with tools like MapReduce, need servers to talk to each other constantly. The key challenge is making sure all this data moves super fast and without getting stuck, even when there are millions of connections. Path diversity just means there are multiple ways, paths, for data to travel, like having several roads instead of one highway. Dynamic scheduling means the system smartly decides which path to use on the fly, based on what's happening right now, to avoid traffic jams. This whole setup helps data centers handle huge workloads, like cloud services for billions of users, without slowing down. As data centers get bigger, these routing tricks are crucial for keeping things reliable, fast, and cheap. Now, moving to the challenge slide. It highlights why old-fashioned routing methods don't cut it in data centers. There's a diagram showing a spine leaf topology. Think of it as a network shaped like a tree. The spine is the core switches at the top, and leaves are the bottom switches connected to servers. First point, east-west traffic dominance. In regular office networks, data mostly flows in from the internet or out to it. But in data centers, most traffic stays inside, servers chatting with other servers for tasks like big data processing or search engines. Traditional routing isn't built for this constant internal buzz. Second, wasted path diversity. Data centers use a setup called spine leaf, which creates lots of parallel paths, like multiple lanes on a freeway, for data to flow. But old protocols, like Spanning Tree Protocol, STP, shut down extra links to avoid loops, where data circles forever and crashes things. This wastes all that extra capacity. It's like building a 10-lane highway but only using one lane. Third, bisection bandwidth needs. Modern apps need full bisection bandwidth. That's a fancy way of saying every server should be able to send and receive data at full speed to any other server at the same time, without bottlenecks. Imagine all cars on the road driving at top speed without traffic. Data centers need it for apps to run smoothly. Fourth, static routing hotspots. Traditional routing picks one best path and sticks to it. This causes problems when big data transfers, called elephant flows, because they're huge, all pile onto the same path, creating jams, while other paths sit empty. It's like everyone choosing the same road during rush hour, even if alternatives are free. In short, old routing is too rigid and wasteful for the fast, unpredictable world of data centers. That's why we need smarter ways to spread out the traffic and use every bit of the network. This slide compares two basic ways to use multiple paths in data centers. It's about spreading data across paths to avoid jams. The diagram likely shows how traffic flows differently in each. First, ECMP, equal cost multi-path. How it works, it uses a hash, like a quick math formula, on details from the data packet, like sender, receiver, and type, to pick one of several equal cost paths. Once chosen, the flow, a stream of related packets, stays on that path. Advantages: super simple to set up on regular hardware, doesn't need to track state, no memory of past decisions, keeps packets in order for each flow, and scales well. Limitations: it's blind to current traffic. It doesn't check if a path is busy. Hash collisions can make loads uneven, and big elephant flows can block smaller, mice, flows, quick, tiny data bursts. Next, VLB, Valiant Load Balancing. How it works: instead of going straight to the destination, data first bounces to a random middle point, intermediate node, then to the end. This randomizes things across the whole network. Advantages: great at spreading load even if traffic is uneven or skewed. It guarantees good performance in worst-case scenarios and doesn't care about flow details. Limitations: adds extra hops, steps, so latency, delay, goes up, paths can stretch to twice as long. It uses more overall bandwidth and still ignores real-time congestion. These are static methods, they don't change based on what's happening now. They're better than single-path routing but can still lead to hotspots if big flows clash. Data centers use them as a starting point, but for top performance, we layer on smarter dynamic stuff. Here we get into fancier solutions. The slide covers 3: dynamic flow scheduling, source routing, and multicast scheduling. There are small diagrams showing paths. First, dynamic flow scheduling, centralized optimization. This detects big elephant flows at the edge switches, top of rack or TOR, which connect directly to servers. A central boss, SDN controller, looks at the whole network, figures out non-clashing paths, and sets them up. Result: way higher throughput, data speed, than plain hashing, because it adapts to real conditions like congestion. In detail, it estimates flow sizes, uses algorithms to optimize, and installs rules. This overcomes static methods blindness but needs a central controller, which might slow down in huge setups. Second, source routing, path encoded in header. The sender, starting server, picks the full path and sticks it in the packet's header as a list of ports. Switches just read the next port and forward, no big tables needed, so the core stays simple and fast. Trade-off, super quick and predictable, but adds extra data to headers, overhead, and needs the sender to know the network layout. Great for deterministic, no surprises, routing in data centers. Third, multicast scheduling, congestion-aware delivery. For sending data to multiple receivers, like in distributed jobs, it tracks link usage to find free bandwidth. It builds smart trees by picking least busy core switches for spreading data. Efficiency, cuts down on flow interference, boosting overall job speed. But again, often uses a central controller, which can be a bottleneck in massive, changing environments. These approaches make networks smarter, adapting to traffic size, type, and congestion for better performance in cloud workloads. This slide focuses on improvements at layer 2, the Ethernet level, where devices use MAC addresses like unique IDs. Diagram shows hierarchical setup with pods, groups of switches. First, modern loop prevention. Old STP blocks links to stop loops, wasting paths. Newer stuff like Trill, SPB, and EVPN use link state routing, sharing full network maps, at layer 2. This enables shortest paths and full multipath use, no more blocked links. Also, multiple spanning trees let different traffic types use different paths. Second, hierarchical addressing. Instead of flat MAC addresses, random and hard to manage, new systems give structured IDs like pod, switch, port. This makes tables smaller, lookups faster, and management easier. Third, edge translation and mobility. Edge switches convert virtual IPs, fake addresses for VMs, virtual machines, like software servers, to physical location IDs. VMs can move around without redoing the whole network, seamless for cloud flexibility. Fourth, link aggregation, LACP. Bundles multiple cables into one logical link, boosts bandwidth, more speed, and adds backup. If one cable fails, others take over. These tweaks make layer 2 networks more like efficient fabrics, interconnected meshes, using all hardware better while keeping things compatible. Wrapping up with trade-offs and what's next. The slide has sliders showing balances and future ideas. Key trade-offs: performance versus complexity. Dynamic systems boost usage but add control overhead, extra work for managing. Centralization versus scalability. Central controllers optimize globally but can choke in giant data centers. Flexibility versus compatibility. Cool new protocols, like source routing, need changes to hardware or software. Efficiency versus overhead. Encoding paths reduces jams but eats a bit more bandwidth for headers. No perfect solution. Pick based on your data center's size, apps, and needs. Future outlook: congestion-aware multipath. Beyond ECMP, using real-time queue and link data for adaptive routing. Programmable data planes. Tools like P4 let switches offload smart logic, enabling fine control in network. Workload-specific tuning. Tailor routing to app types, like AI, needs low latency, versus web search, needs high throughput. In the end, data center routing has come a long way from basic setups. It's all about smartly using multiple paths, adapting on the fly, and squeezing max performance from hardware. As clouds grow, these innovations keep things running smooth and cost-effective. No single fix works everywhere. The future is about adaptable systems. Thanks for listening. If something's unclear, think of it like traffic management in a busy city. The goal is no jams, full speed, and using every road wisely.